Today I'm thinking about explaining Planck's equation for small wavelength decrease to zero as a replacement by non-photon penetration behavior. Now, we all know that Planck's constant is very different, okay? It explains the most basic parts of quantum theory. It's the first step that came up with Planck's constant h, which is the unit of measure for all these tiny equations. However, the basics of that equation over here on the left is quite different for two different reasons. First, the classical theory, which is by Boltzmann's constant, that's here's kV, is in strength, and it would say that the amount of photons generated keeps going up as the wavelength goes down. And it keeps going up, and it would go up accordingly to infinity. But that's not what happens. Instead, it depends on the temperature. This is 3,000 Kelvin or 4,000 Kelvin or 5,000 Kelvin. You get a distribution of different volumes, intensity of wavelengths. Now, when you're up at, 200 Kelvin or 300 Kelvin, say the normal range on Earth, standard room and temperature, you're way over here, and guess what? That black line and the line for that are exactly the same, because at that point, you're not doing any most stresses. The only thing that happens is those molecules are outer shells of electrons that are sort of moving around so fast they can't bond, and then they bump into each other, and that keeps them apart. And as they bump into each other, they create a photon. And that's the formula, the Boltzmann's constant. However, the reality is that it goes up, it reaches a peak, and then goes down to effectively zero at some small distance of maybe 0.2 pentameters. Sorry, I have to get that. So I'm going to show you that it's very different. That instead what's happened is this is how much would be created if it was all the energy was going into photons. But eventually what happens is that gets replaced by the ionization. So that outer electron, instead of bumping, actually goes inside. Of course, if it goes inside, there's no stress to create the photon. Now that's really weird, because ultimately the procedures of quantum theory, okay, predict this line, the blue, all the way up perfectly until there. And in fact, Einstein in 2005 in his Heuristic Light paper, the one that got him the Nobel Prize, says, we therefore arrive at the conclusion, the greater the density, the more useful these principles are. So this divergence becomes better known. However, these principles fail completely to explain small wavelengths and the small radiation density. That is, he doesn't predict this, and I'm going to show you how to do it. Now, to do that, instead of thinking of Planck's as one event, the photon generating, I apply two events. There's an inward stress as those two molecules come bumping into each other, but also if that lead electron gets inside, for the moment you basically get a supermolecule, and it sort of goes up an outward push for the combination, which is no inward stress. So if this approaching electron pushes that inward, there's a little inward stress, and to relieve that, the photon gets this rotating latitude stress moving at the speed of light comes off. But if that actually gets captured, this whole structure gets a little bit bigger, which means there's no stress and no photon. And that is that if you take this equation here, the Planck's equation, and you think of this E section, that is the attenuation of bump a little more, bump a little more. It's a series of chains of bumping until you get a random description over a whole bunch of different bumps. Well, that's this curve. But instead, the one event would be without the e to the power. That would be hv over kv minus 1. But here, I think about it as hv minus kb over kb. That becomes the 1, and that becomes this ratio. And so what happens is that the normal kbt is the creation of photons, as if no matter what happens, it would keep creating photons all the way down until the outer electron is touching the nucleus of the second atom, which can't happen, okay? And then what happens is hv becomes the energy of that photon here, and one by one, as this happens, that releases that amount of energy in step-by-step procedures as one electron gets pushed in and then the photon releases. Now, let's look at that now with this revision. You see the policies of what they're talking about in a density at the time of Einstein, and that his comment says that this graph, this is the Planck's equation here in yellow, would keep going up. It would be different than Boltzmann's constant here in this orange burgundy, but it would be different, and it works perfectly up until that. And what I've added is this gray line, and that is the idea of a balance PV equals HT and HT, and that's the subtraction that we get in the last screen. So the fail happens, but really that means this curve is minus that one. And because that energy level, the H level, is so much smaller than KB, you basically get a curve that then drops to 0 because this one's going to infinity, but that one's going to infinity, but this one's going to infinity and crosses way up here. And I've marked that as a scaling to 1, that cross point. Okay? Now, where do those penetrations occur? So what I did was when you do PV equals NHT, the distance of that interaction, that wavelength, okay, obviously it's squared because of the Rydberg equation. Basically, it becomes 8/7 times the Bohr radius. So that means that the same thing that happens, just like when electrons are trying to balance at the Bohr hydrogen radius, the same thing happens when the electrons approach and they get closer than that, they get captured instead inside, and the volume does not become a photon generating, but becomes a temporary super things. So you can think of this. You've got a big shell of electrons. As this stress comes in, it pushes that electron in, but there's not time to resolve that, so that field pushes this one out in the same amount of time. Yet, at the small bandwidths, that electron penetrates, and this blue set of two things suddenly become combined. And in fact, they actually get slightly bigger here with this hashed line. The outer electrons get enlarged as a set temporarily, while the super molecule temporarily occurs. But that only occurs if you have a whole bunch of energy to get that electron pushed all the way in here to that same Bohr radius ratio. Now, that leads to some very interesting things, and probably the most challenging slide of my talk, as I gave it here at the Texas APS presentation. We spent 90% of the questions were on this slide. That is, if you take 1, and you take gravity, and you take Boltzmann's constant, and you take Planck's constant, okay, those are theirs, and I adjust them by 3/2 and 8, which is 2 to the 3rd, and that is basically the conversion of 1 over distance squared to 1 over distance cubed. That's the 2 versus the 3 that's thrown by those combination of those two integrals. And the 2 to the 3rd, which is that field, 1 to the distance cubed, but applied for the duopoles, okay? Because an electron really has 2 poles. That's why it has a 720 degree cycle, because you're actually seeing two Dirac duopoles locked at 180 degrees. One's here, one's here. So along this axis, the axis of symmetry, which you can see with longitudinal rings of electrons and all sorts of other places, there is a symmetry to molecules. Anyway, so when you do that, you get a refined constant here, and that graphs here. And the calculation per the program was 0, but it is 0.9999, 4 nines. This is nearly impossible. There is no way that 3 constants for the exponential scale can be this closely related unless there really is a meaning for gravity to be related directly to Planck's constant. Gravity is not independent. Gravity is Planck to the 1/3 power. Now, why is that? That's because fields come with equations, and their strength is based upon position in the field and basically a slope. That slope is, let me explain it a little. That slope is a curve that has really 2 important parts. The one is the Bohr radius, a sub O, okay? That's where both of those are equal. Otherwise, you wouldn't get a 1 proton, 1 electron system to have a basic balancing distance. That distance is the Bohr hydrogen radius, okay? However, its full strength gets up and up and up by 1 over distance squared, and at the particle edge, it's at its maximum. Energy cannot go to infinity because once it goes to the particle edge, who knows what's going on inside to build up that energy? And we don't know at that point, or at least I don't. And so at the particle edge, its full strength is A sub O over R sub E, the particle edge distance, that's the, and to the squared. Now that's well known because that's actually the square root of that is called the fine structure constant, and usually put out with the symbol alpha. And so as you do that, the difference between squares gets you charge. The charge, Q, equals H times A sub O over R sub E squared, okay? Now, when you move to fields, you're moving up the stack. And so that's the derivative. So that's 1 over distance cubed versus 1 over distance to the 4th, okay? So the electrostatic field is 1 over distance cubed. But guess what? There's that counterbalance, the thing that's making that Bohr radius. Electrostatic and extra 1 over R. They call this angular momentum, but I call it extra 1 over R, or radial nucleostatic. And as a field, this one is 1 over distance cubed, and the push has attraction, and the repulsion is 1 over distance to the 4th. When you put those together, the ratio, the relative strength of that is a ratio of 4 over 3, an exponent of 4 over 3. And so if you take the total strength of the gravity field, that is Planck's constant times 4/3. And when you have an electron shell where you have the nucleus and the electrons, you basically have reversed that process. So you're taking the 4/3 minus the 3/3, the basic Planck constant, and that leaves you with the 1/3. The reason for gravity is not independent. It is directly related to Planck, and it is based upon the cube root of that when properly scaled by these 2 factors. With that, you'll have a totally new understanding of the Planck's equation understood by this combination. And you'll start to have an understanding for what's going to come next, because this leads to relativity, to magnetism, to elementary particle masses. All of those are based upon these ratios, the 2 over 3, the 3 over 4, the exponents of those, and as you do the derivatives and integrals, the constants that are thrown of those. Those will be covered in different sessions. Thank you.